the value of good health, a non-parametric approach to developing EQ-5D-5L value sets. So value sets are the set of values we might assign to every possible utility or every possible health state that a person could report being in. Now, this is joint work with my co-author Feng Xie. I started this work as a postdoc with him, and we are now continuing this work in a EUROQUAL group supported project where we now look at international data sets. Today I'll just look at the Canadian population study. I'm going to motivate what I'm doing first with a bit of a case study. So this is a health case study. It says, suppose you've been approached by some public health insurer for some small country for advice. So there's a special interest group that insists that this public insurer should adopt a new treatment for some condition that affects, say, 2% of the population each year. So there's an existing treatment, we'll call it alpha, there's a new treatment, beta, and they're equally maybe effective at reducing symptoms, so about equally effective, but the manufacturer of this new treatment, beta, says that their new treatment is better because it involves a once daily pill instead of a weekly injection. So what do we do? How do we quantify that? So beta costs $2,000 per year per patient, for example. Alpha is maybe $1,040 per year for each patient. So there's a difference in cost, but we're saying that there's some difference in these two treatments. So there's this public health insurer, limited resources, what do you do? So one common approach to problems sort of like this is to use something called an incremental cost-utility ratio, where you just compare the costs of your new treatment to the old treatment and the utility of the new treatment to the old treatment, and we'll construct something called a quality adjusted life year. You might have heard of this before. Another way of referring to these you might hear is an ICER, so an incremental cost effectiveness ratio. Now, what we need in order to use this formula is a value for these U, for utility. As economists, we talk about utility all the time, but we very rarely put a numeric value on utility. So in the health field, there are a few ways that people have gone around about assessing utility. So one of those is the EQ-5D. That's a patient-reported outcome measure. All of these are, in fact. But the EQ-5D is one. It's the one that I'll look at today. There are others. So there's one called the ARE-UWA and one called the SF6D. So these are patient-reported outcome measures where you ask people how they feel about their health or ask them to rate their health. And then there's some number that we're going to attach to it. So the point of my talk today is how we might go about assigning numbers to different health states that people might report. So the difference in utility values here can be very important for funding applications. So if we have a large difference in utility, we're going to be implying that it costs a lot per quality adjusted life year, and a small difference will be lower. Sorry, flip those around. Rough night. So we want to fund interventions that have lower cost per quality adjusted life year if we want to maximize a healthcare budget. So there's some discussion about what the number is. There's a set number there might be. So $50,000 per quality has come up in some places, now debated to be around 100,000. Now there's another study that tries to go in the reverse and estimate what the cost per quality is in Australia, and they estimated that is about $28,000 per quality adjusted life year when the government spends money on healthcare. So interesting study there. And I'll continue. So the EQ-5D-5L, it's the EUROQUAL 5-dimensional quality of life scale in 5 levels. So there's also a 3-level variant, but this one's in 5 levels. So there are 5 dimensions of health. So if you think of health, it could be a lot of things, right? But we're going to simplify this down to just 5 dimensions, if that's possible. So I'll just go through what this survey looks like. So if we are a patient, for example, in a randomized controlled trial, we might ask you before you start a new treatment, okay, how do you rate your health today? So I'll ask you, how would you rate your mobility? And you have 5 options. So no problems walking around, right down to I'm unable to walk about. Then you go to self-care. Are you able to take care of yourself? Right down to I'm unable to do anything. Next 2 dimensions are usual activities and pain and discomfort. And then the last one is anxiety and depression. So it's like 5 ways to describe your health state. So it is a generalized measure. It's not specific to any particular health condition. So you can understand the appeal. There are other ways that health states are actually attempted to be valued that are more specific, but not all of them give a utility value at the end, so that it's not to be used in a health analysis or a health technology assessment. So if we're to use this assessment tool, we might run this alongside a randomized control trial. So we'd collect treatment responses maybe in each treatment arm, maybe before treatment, during treatment, a few points during treatment, and after treatment. So if we do this, there are 3,125 possible health states that a patient could report experiencing. So there's a level for each of those 5 dimensions. So just to set this up, 1, 1, 1, 1, 1 is a state with no problems in any dimension, and 5, 5, 5, 5, 5 is the worst. So there's severe problems in every dimension. So each state, we need a numeric value for that state in order to have a utility value. So 1 is going to mean fully healthy, and 0 is going to mean dead. And less than 0 indicates a state that is worse than being dead. So that's possible here. So let's look at how these values are generated. So we're not, like, if we just give patients this survey, we don't get a number back, right? We get 1, 2, 3, 3, 4, or something like this. So where are we getting these numbers from? So what we're usually going to do is draw a population representative sample, where we're going to ask a sample of people to report preferences to a subset of those health states. I'm not going to ask you 3,125 reports, obviously, but I might ask you to value 10 health states, which is standard with the EQ-5D. So then we're going to the way we're going to gather your preferences now also is to use some kind of a preference elicitation instrument. So there are a few of them out there. You could use a discrete choice experiment where you ask people, you have option A, you have option B, which one do you prefer? Which one's better? You could have a standard gamble where you say, suppose there's this possibility that this happens, there's this other probability that this other outcome happens, which outcome do you prefer? And another way you could do this is with the time trade-off. So I'm going to look at time trade-off results. The EUROQUAL group, when they assess, when they draw a population sample, they do 2 things. They actually do a time trade-off, and they also do a discrete choice experiment. I'm just going to look at time trade-off results for this study. So this is what it looks like to a patient. We actually start with both bars filled in, and so the bottom bar is some health state. So it's described here, you have severe problems walking about, moderate problems washing or dressing yourself, moderate problems doing usual activities, no pain or discomfort, and extremely anxious or depressed. And then you say, okay, so suppose you have 10 years in full health and 10 years in this other state. Which life do you prefer? And if we're starting both bars at full, we say, okay, well, I want 10 years full health, right? And then you just cut back a little bit. So maybe we'll take a step back and say, okay, now you have life A and B, but there's less time in the healthy state. Which life do you prefer? Well, if you're at 90%, 9 years out of 10, you might say, oh, I still prefer life A, even though I've sacrificed a bit of time. And we keep doing this until we get to the point where a participant or a respondent says, oh, I'm about indifferent. You say that they're about equal, and that's going to be our value.
Excuse me,
yes.
The 5-year study, is that from the present? That from present time, or how do you count that? Is it like from now plus 5 years, or from now plus 10 years, or
yes? So there's
a certain point in time plus 5.
Well, there are a few ways of doing this actually. So there's a bit more details to this, but it's typically suppose you spend. They usually start with suppose you have 10 years in full health, and then this health state comes, and then you will spend the next 10 years of your life in this state or the other state. So there's actually a lead time component so that we can value negative states, but it is from how you would value this hypothetical state right now. So you're not experiencing the state is the I guess the main takeaway.
If you're 25 years old, if you're 65 years
exactly,
old,
absolutely.
Okay.
This is by no means a perfect measure, and I would say in some of the other work that I'm pushing into, I'm very interested in how can we sort of reduce this hypothetical bias that you're picking up on, like and also the temporal difference. It's not a perfect measure. I'm not advertising it to be so. But it is perhaps gets us closer to something to use, but it's certainly not covering all of the answers. Okay? All right, so now the utility values, as I said, it's a very simple now breakdown of what we do with that trade-off. So we take the utility of dead and assign 0 value to that, and the time you spend in the dead state was like 0.5 up there. The utility of the healthy state, we peg that at 1. So that's the maximum utility you can have. And then utility of ill, we don't know. So we're going to infer that, and we just put it in a very simple additive formula to infer that the utility of ill is just the ratio of the time spent in the 2 states. So that's a number, right? Get a number. So not all of the 3,125 states were sampled, though. So we're going to use those collected values from our population sample. It usually needs to be at least 1,000 people. These studies range from 1,000 to about 1,200 people typically. So we'll use those values to now estimate the states that we didn't collect, is the idea. So common approaches that are encountered in the literature. There are about 15 of these studies published so far, each for a different country. So mostly parametric approaches. So you see main effects 20 parameter dummy model. So every dimension and level of health is a dummy variable, and we'll just feed that in. So that's a main effects model. Then there are selected interactions you'll see appearing in these models. Differs across different populations. So there are different algorithms essentially that show up in every country. You see also a Tobit model sometimes. So there's a censoring at -1 in this model. So we don't maybe observe the true preference for less than, so worse than dead health states. And then there are a few multiplicative models that have been argued for that are linear with some multipliers on the end. So on the nonparametric side, there is also a Bayesian framework, so a nonparametric Bayesian framework, which has been suggested and has been run for an EQ-5D-5L set. So that's where you only have 3 levels of health for every dimension. Now, in theory, what I'm proposing here with the nonparametric should converge to the Bayesian model. Now, the difference here is that a Bayesian model still requires you to specify a functional form to get the model started, and it requires you to have prior information. So you need data from either another country or another place to get that model started. So if you don't have that information, or you don't know what model to specify, so one of the things I'm sort of saying here is that the interactions between the levels and dimensions of health could potentially be quite complex. So if you are to write these all down, we already have 20 parameters for just the main effects, and then to write down all of the possible interactions is going to be quite a task. And if you don't know where you're to start this, I mean, you could be there a long time. So as I'm suggesting, a nonparametric approach sort of cuts through that. You run it once, yes, it takes time, but you run it once and it can give an indicator. And because any parametric model is actually nested within the nonparametric approach, if you actually had a correct parametric specification, you would get the same result. And it's almost like a robustness check. So the last thing also that's appearing in this literature a little more are hybrid models, where we take the DCE data and the TTO data and try to combine them in some way. And they're typically, you'll just see a linear combination type thing of the DCE results and the TTO results. So you see a linear model and a logit model, and they're combined with a parameter. So maybe an opportunity to move into how to combine the results from these two. I'm not doing that at this point. Okay, so the summary here is that overall, the models tend to vary based on what types of interactions are included in them. There is a strong preference for parsimony, and actually a small preference for a model, a preference for reporting coefficients, so that you have the users of these data sets actually calculate the utility values for each of the health states. So that comes up later, because in nonparametric regression, we don't get coefficients. So I can't report to you a list of coefficients, I just have the values at the end. So there's a sort of a paradigm shift in how you would look at the results and how you might use the results. So in this project, I'm using nonparametric regression to generate estimates for the unrecorded states. So I'm going to use the data that we recorded as training data, and I'm going to train my algorithm, if you will, on that data, and then use it to predict over all of the unsampled states. So there's no model specification required to do this. So I don't have to say, okay, I know a linear relationship, there's alpha, there's beta 1, there's beta. I don't have to do that. There are fewer assumptions about the data generating process. So I don't need to know that the errors are normally distributed, for example. They don't have to be normally distributed. And that's kind of nice, because this data does not look normally distributed for most of these health states. Any type of interaction between these dimensions and levels is completely possible without me saying anything. So I have much less room to make a mistake, leave some interaction out, put something in that doesn't matter, and mess up the model. There's no prior data required here, so that's kind of nice. If I don't know another country's data set, I don't need to. And it's robust to outliers. So unlike a linear model where you have a few outliers and it starts to skew the slope, this the technique does not respond in the same way. So that's kind of nice here too, because as you see in this data, some people like to report that they're in perfect health all the time, and some people report almost every health state is worse than dead. So we have lots of variance. Okay, so the study overall, I think I did distribute the paper. If you had a look and you have comments, I'm happy to hear them. So we compared 12 models for the Canadian valuation study. So there's a main effects linear model, and this is the preferred model that was reported by the original co-author, the original authors of the study, one of which is my co-author on the current study. There's also a main effects 20 parameter model, which is reported in almost every paper. They kind of start up with this main effects model. And then I also include an 8 parameter multiplicative model that's reported by Rand Hendrickson, who compared a few different value sets. There are other models that were reported in that paper. I didn't find them to perform any better or to substantially change the problem, so I'm just using the first one as a comparison. And then I'll also have nonparametric local constant regression. Okay, so there's 4 comparators there, and then I'm going to throw 3 other things in the mix here. So I'm going to look at just the health states, so mobility, self-care, usual activities, pain and discomfort, anxiety and depression. Then I'll put in individual effects, so do individual respondents affect the result? And then I'll also include the effect of interviewers. So in the literature, there is some talk that maybe the interviewers who are conducting the TTO task might influence the results. So I'll put that in there and we'll see what happens. So now I'll run all 3 of these variations for all 4 of those options. So 12 comparisons. Part of this is really to demonstrate to the crowd, if you will, that the method, what it can do and what it looks like when compared to other models. So the key results now. I'm still on time, so that's good. So local constant regression with the individual effects is outperforming any other specification in sample, and we would expect that. So in sample, we get a better fit, like 80% reduction in mean absolute error over the next best model. Average squared prediction model, 95, almost 94% reduction. And the Bland-Altman critical value there's a 76% reduction. So that's a technique for comparing 2 estimators and how they perform against each other. So this main effects linear model with the individual random effect seems to be is the best performing parametric model. So interviewer effect didn't add anything to the performance here. We just have this non-parametric local constant, very basic setup actually for a non-parametric model that is performing much better in sample. But the next question you might ask is, well, maybe you just overfitted your model, right? So maybe you have poor performance out of sample now because it's overfitted. I did find here and mentioned here that the individual effects are essential, and some of the standard techniques for predicting out of sample when you have individual effects vary with the models. I'll just use like the main effects, the main coefficient effects, and sort of get rid of the individual effects. So for my local constant predictor, I actually go and integrate out all of the individual effects by comparing every possible interaction and taking the average of those. So it's a brute force integrate out that individual effect when it comes to predicting out of the sample. So now we'll look at out of sample results. Also did very well. Wow. So the procedure I used, which differed actually from the literature here, so the literature actually was in sample as well. This literature does something very different. They say that we should just look at the mean value in each cell and take the difference between our estimate and the mean value that we recorded for each health state. And typically that's not what you would do when you use statistics. You'll look at the difference between every observation you have in your sample. So that's what I've done here. It is a different number, but I did that, and I think I also reported the other results that were more standard in this literature as well. So the cross-validation procedure I used here is to randomly omit 10% of the sample. I didn't choose to randomly omit health states, just randomly omit 10% of the possible observations here. I repeated that 1,000 times, and then again, our local constant regression did a lot better. So significantly outperformed every other specification, 95% lower on the expected average squared prediction error. So for every sample, I calculate that average squared prediction error and then take the mean across all of those 1,000 replications. The same for the expected mean absolute error, 81% lower. So like stunning. The next question you might have is, well, like what did you do wrong, right? So if the results are this different, what happened? It's probably the knee-jerk response here. So there are a few other ways as well that we might assess how well this model is performing. So for the EQ-5D, monotonicity is something that they're very interested in because it's a health preference measure. There is a natural ordering to some, not all, of the health states. So if you have health state 1, 1, 1, 1, 1, that should obviously be better than any other health state. So the value predicted for that state should also be better. So if we compare all the possible pairings where that's true, where there's one state that's clearly dominant to another, we would like them to match up. So we like them to be consistent. I didn't give any specification or any form to this model, and it produced no inconsistent pairings, which was actually quite surprising. Because this isn't, in the models that are in the literature at current, that the desire to constrain the model so that this is true is definitely a part of the model specification procedure. I haven't done anything like that. I've just let this model run, and the results match what was expected. So they're consistent. They're producing a value set which is consistent with, okay, this health state is actually valued better than the other overall. So even with all of the predicted results. So another thing that is done in this literature is to look at the minimally important difference. So if we take all of the health states that are nearby, so every health state has 10, or sometimes less if they're on the boundary, but there's 10 health states that are one step away in one level. So if we take the average of all of those and sort of combine them together, then the local constant regression has the lowest minimally important difference of all of these measures. So it's more sensitive to changes in utility overall. And you can you recall that when we're looking at that incremental cost utility ratio, the difference actually makes a difference. Right? So if we have very small differences, it's going to relate to larger quality adjusted life year costs. And finally, some pictures. So a Bland-Altman analysis here. So this takes the mean between the two measures estimates and then the difference on the y-axis. So the mean and the difference. This is an older technique, but I felt it was quite appropriate. I'm not looking at like the correlation coefficients or anything here. This is just a bit more useful when we have two measures that are attempting to measure the same thing. So overall, we see that some health states, so health states that occur outside of the boundaries, are significantly different from that best performing model, which is this local constant model with an individual effect. We can see that when I included interviewer effects, they're very similar, so the results are still very compressed. But every other model, the results are quite dispersed, and sometimes it's in a significant manner. I've also included the minimally important difference as the shaded area. So here, it doesn't show up as well here. But you can see that what this says is that if we use all of these different models are actually producing different final values that could actually be different in a substantive way and in a significant way. So it's not like I've run this model and okay, the values are, it does something different, but it's not meaningful. It appears here that if we choose a different model over this best performing one, we could get a result that actually is different in a meaningful way. All right, so that's fine. That's half of the presentation. So I have this great picture of a car because at this point I'd like to just go into, okay, so how does nonparametric regression work? So like look under the hood of what's going on here. And nonparametric regression can be applicable to quite a range of applied problems, like problems where you don't necessarily know the functional form, or you wonder, like, what are things doing here, and you want to do a sort of exploratory analysis. It's not the same as data mining. If you have an output and an input, so you have all your exploratory variables and you have your output, your output variable, then data mining would actually say, I don't know what the output is. So I'm going to go and I'm going to run a bunch of algorithms. I don't know what they're doing, and I'm going to sort of see what's there. You know what's there. You actually are applying a structure to this model. So I'll go through what that is because it's quite different than the standard regression. So the overview of this is that we need to identify some optimal bandwidths. Bandwidths are, if we take a point, how much information around that point should we look at as well? Then we need to use those bandwidths to generate estimates using a kernel function. So every explanatory variable, every dimension of health will have a kernel attached to it, and we are going to multiply those kernels all together into a product kernel. So I'm drawing very heavily from Li and Racine and Ouyang et al. This is not a new technique. So it's been around for a little while. There's a certain hesitation, it seems, though, for people to really jump in and use it. Not that no one has, there just seems to be a bit of a hesitation. Oh, yeah. Okay, we skipped to the end somehow. Again? All right, I'll just back up until I find it. Don't do it again. Okay. So, yeah, so what we're trying to do here is estimate our outcome. So our outcome is a utility value. And we have some functional form, G, of xi. The xi's are the dimensions of health, and we'll also include like individual effects. And then we have some error. Okay, so I'm just going to, rather than say alpha plus beta M mobility and beta 3 self-care, I'm going to say I don't know what the functional form is at all. So let's go find what it is. I have data, I have inputs and outputs, but I don't know what the functional form is. And I'll just assume that the expected error, the conditional expected error is 0. Yes.
So we are assuming that there is no theory behind our expectations.
I wouldn't say that there's no. Well, okay, so the econometric theory of like, oh, we're going to assume a distribution of the errors and this, no, we're not doing. But it's not theory free because we still have structured what is going in our model. There's quite a talk right now with machine learning literature right now, and yeah, we still do have some structure, and the relationship between our variables is still present. Okay, so each explanatory variable that I'm putting in our model here has a kernel. Now, the kernels don't matter that much, actually. You can change the kernels. There's a few to pick from. They don't influence the results as much. But how the kernel works is if we take a particular xi, we'll call it a health state, and we'll consider all of the other health states in the data set, and we'll use a kernel to say how much weight we give to all of the other values in the set of observations. So the lambda informs us on how much weight to put on all of the other observations. So how far should we go? So we have a weight function, but how wide should the weight function be? And the lambda are the most important points. So if the lambda are really wide, we're doing something like smoothing. If we have a lambda that takes up the entire range of our data, we're essentially saying incorporate all the data when we generate, say, a mean value. So you're saying there's one value. There's a mean for that variable, and there's just one. If we have a very small kernel, so the lambda is very small, we're saying we have very small views, very small snapshots of this variable, and we're going to calculate, say, a mean, a weighted mean within each of these very small bandwidths. So larger bandwidths means the variable matters much less to our outcome. Smaller bandwidths means it matters much more. So here we need to find 5 kernels in total, one for each health dimension, and any other variables I've included. So we'll also find a kernel for individual effect. We'll find a kernel for the interviewer effect as well. So the product kernel just takes all of those small kernels and puts them together. Fine. So again, which I've said before, we're looking at one reference health state and considering, okay, all of the other health states in our data, we're going to smooth to them. We're going to use a kernel to apply weights to all of the other data, and we're going to find how big that weighting function should be. So how much data are we looking at? How wide are we going? We also will, for this technique, need to estimate the probability of observing of each observation occurring. So this is what we're trying to estimate here. So we're trying to estimate this unknown specification. We have utility in here, we have that product kernel, and the product kernel actually appears on the bottom as well. So the way we're going to go about finding those bandwidths is to use a data-driven process. So this is where I'm using the data I have as a training set. So I'll find the optimal bandwidths by doing a cross-validation function. For every observation I have in my data, I will omit one observation and calculate this utility minus what I have here. So this is very computationally intensive. So in this data set, the largest model, the one with interviewer and ID, took 3 to 4 days to run. That's nothing. Okay, I have a model now that took 8 days to run. But that's fine, right? And you get bigger data sets, and this is what your computer was made to do. It's a little bit different way of looking at data analysis for some people. You expect you click the button and you get the result. But this is what really is, your computer was made to do this, right? So we're using the power of the computer to do this now. So this cross-validation function, you'll notice, is actually minimizing the mean squared error. If we look at this here. So that minimization process is actually trading off bias and variance now. In a linear model, we might say it's the best linear unbiased estimator, right? So we're not saying that here. We're saying trade off these two things such that we minimize the mean squared error. So there is no surprise now that these models do so much better in sample. It's out of sample where we might say, okay, maybe something different went on. So how can they predict when we get out of sample? So it is sort of like a supervised learning. Our sample data is the training data, but we also have the outcome. So it's not the same thing as data mining. So the bandwidth results for my best performing model are here. These are not coefficients. These are the widths of the data to include. Something that would be a giveaway, that something to be concerned about, is any of these bandwidths were really large. So if we have any bandwidth close to its upper value, we know that this variable doesn't matter. So one of the nice things about this cross-validation process is that variables that don't matter are essentially smoothed out. You don't have to go through a variable selection process to sort of, okay, does this matter, does that? Because it just happens automatically.
And the type of kernel?
This one was a Lee Racine kernel that I use for all of the main effects, and HS and Aiken for the individual effect.
And your view is it doesn't, but in practice it does matter?
The kernel, this particular kernel weight function matters very little. The bandwidth matters a lot.
Yeah.
So it's a selection. If you use a plug-in rule, or you just pick a bandwidth at random, it makes all of the difference. Because again, a big bandwidth says, okay, include all of the data and just estimate one value for a mean. And a small one says go everywhere. And do all of these small things. So it's the bandwidth that matters much less than the kernel.
And your ID dimension there, that's the interviewer?
This is actually the individual respondent. So I have 1,073 in this sample. And it's just like a categorical, not ordered or anything. Okay. Okay, so I don't get a table of coefficients here, right? So one thing I can do, if I have time, is I can provide, say, in my journal submission, a link to a website that's hopefully interactive. Oh, reload. Okay, hopefully interactive and that people can work with. So I can give some plots of the data in one dimension as best as possible. So we actually have 6 dimensions, 7. Here, you could try. Doesn't work too well. But so here, what I've done is just plot all of the health states using like an R-Shiny package. So this is the predictions of the health state values, all 3,125, and they're sorted by the magnitude of the best performing model. So that's why there's this smooth black line, and I've allowed users to go and specify, okay, when we look at a different health state, so look at 2, 1, 1, 1, 1, here's the estimates from all of those models, and here's the location of that health state here. And then I can go and change what models I want to compare. So if I compare that MELT model to, like, say, the LC model, I can compare 2 at the same time even. The next thing I need to do is, because I potentially have... Yeah?
So the black line again?
This is the best performing model, so the local constant with individual effects. So that's the magnitude. So I'm just going to sort based on that one. So the black one.
The individual dots are the estimates
from the other models. So these are the estimates actually from that best performing model in the magnitude they occurred.
So nobody's going worse than death. Or very few of them have done worse than death?
Yes, very few at the end, yes. In the model. So in the actual data, there's lots of variance. Lots of people select that. So these are the estimates over the whole sample. In the actual data, people select all kinds of things.
So the reason that we're not seeing that tail go down underneath is because there's no consistency in the way people would choose which ones they were choosing as being worse than death.
It could be, or it could be just overall that there are a few, so they're just not very. So let me think of one where there's more. Maybe Med 1 will be a little bit more sensitive. So this model, so here we have a few more that come down lower, starting from here, but it's very extreme health states, where the mean value or the prediction actually gets pulled sufficiently down that the state is worse than death.
So that's different to other estimates where quite a big part of the tail usually heads down to worse than death. I'm thinking about looking at some of the other ones in terms of where people think they're going.
Mm-hmm.
Quite a lot of the states do turn up being valued as worse than death.
So these are could be. This is the actual estimates from that model. So the model where I say Med 1 in this particular population sample, these states actually came out as negative. We can talk more. I can even send you a link to this. Okay. So the other thing I can do is that because I have policymakers who now are in the setting where they're used to getting a formula and plugging numbers in and calculating a value for each of these health states, I have to think differently about how I express the results of this. I don't have coefficients. So what I've done here is provide a link to an interactive site where you can actually download all of the estimates that came out of the models, or you can just select a few, and you can also select what health state you'd like to look at. So you could just select 1, 1, 1, 1, and you get this across every model, and you can actually unselect what models you don't want to see, and they just disappear as well. So I'm trying to make this user-friendly. I'm trying to make this applied, although it's a complex sort of topic to deal with. And there it is. Okay, that'll work. Okay, so the future of this project. Like I said at the beginning, we're trying to incorporate the TTO data from other countries. I right now have a set of 8 countries where I can now do a regression model that incorporates all of the data from all of those countries. So you get a much more robust estimate when you have more data. The interesting result there is, does country matter? Is it really that people are in different countries have this substantively different preference for different health states, or is it something else? You can see different biases. So different countries, you will see overall higher evaluation of some mild states or lower evaluation of lower states. But is that endemic, or is that something to do with the algorithms that are being used, or what's going on? So that's where this project is going. I also compare modeling strategies in that project to nonparametric local regression. And in the long view, I guess the nonparametric regression incorporating the DCE data and the TTO data could be interesting, but I have not started in on that myself. So in summary, these patient-reported outcome measures are this foundational component in health technology assessment. This is what many governments around the world do to assess whether to incorporate new drugs or incorporate new technologies into a public healthcare system. Some way of ranking and evaluating what to pay for. So you can see that there are some fine aspects of this process of how we get these values to use that could be substantial. I mean, they could affect the outcomes here for what technologies actually get funded or don't. So the generation of these valuation sets is based on population preferences. They're typically not taken from people who have experienced that health state. And honestly, it's probably not possible you've experienced all 10 of those health states that you are exposed to. So there's obviously a pretty big room for hypothetical bias if you're concerned about that. On the other hand, you might argue that these valuations are from the general population. And it's the general population who's going to evaluate whether it was the right thing or not to do to fund this or that healthcare. So not all health states can realistically be assessed by the population. It's not like we can ask everybody to value every health state. So we need to use something to use a small subset to get values to evaluate. Okay. Now, nonparametric regression suggests that interactions appear to be important. So a basic model, you see a lot of the algorithms differ based on what type of an interactive effect are included. The strong increase in the results, like the better in-sample, out-of-sample fit, suggests that there is additionally more complex interactions going on here between the dimensions and values of health, which is pretty widely accepted by people who use these measures. The value set is better in and out of sample. And the value set that is produced gives relatively higher values for more severe states, so less bad, and relatively lower values for milder states. We're compressing the range of values somewhat when we use this nonparametric approach. So that would kind of suggest also that these parametric models are a little bit more sensitive to the tails of the data. So using these other value sets for policy could lead to over or undervaluation of treatments. If we were to use a particular form for a value set and use all of those values, we might value states quite differently. My last note is nonparametric regression maybe looks scary, but it's pretty simple to implement if you've never done it before and you have a data set. I use a nonparametric package that's embedded in R, and it's like these 2 lines, and then also there's a significance test you can run. So it's very compact, even if it takes you 4 or 5 days to run it. You know. So that's automatic value selection with those two yes.
lines, or you have to do something else?
No, this first line here, this bandwidth local. I've just named it. So this generates the bandwidth, and this actually estimates the model.
Yeah.
So those variables are categorical variables.
These ones are ordered categorical variables. This is just categorical. I said local constant. I said used cross-validation least squares. There's also a cross-validation maximum likelihood. I did least squares. And I specified some data. And then this is very simple. These 2 steps can be put together. From an applied perspective, I think that this is the better option because this is going to take a long time. This takes hardly any time.
Does the individual experience with specific illnesses, is that an important factor in how they evaluate?
That could be. So in these health states right now, they actually collect, usually there are some other demographic variables that are collected. They're not used in the generation of the final value set. They do ask all the respondents to rate their own health today on a value score. So rate your health on this thermometer thing that's 0 to 100. It's not actually incorporated in this data. So it's something that I have some data now, and I will, like to look at.
That could have a big impact.
Absolutely, yeah. There are other things. So gender's not in this.
And perhaps other things like, are they insured, not insured? Are they,
Sure.
All sorts of things. And what kind of geographical area? They're very polluted area, or they might have a
Yes.
perception of, or not.
Yeah, so some of those things are not included, but could probably be backed out from other data if you could do so. So the data I have now with 8 countries, that was not entirely easy to put together. It wasn't totally hard, but there are other countries with data that are not so willing to share. But yeah, more data works better. And if you're going to use this, in my opinion anyway, if you're going to use this to gauge public health policies, it's in our best interest to really spend some time and look at this very carefully.
Okay, thank you.
Sure.